Wrong according to Sanskrit. It should be. If Hindi is derived from Sanskrit, then that is wrong. This is 6th lecture in 110 and today is 11/1/94, and our topic would be signal waveforms. What we are going to discuss today are the various kinds of signals that arise in electronic circuits. And the general topic is signal processing circuits. As part of this general topic, signal processing circuits, we shall first discuss some of the signal waveforms. It is important to understand what a signal is and what processing means, so that we can devise electronic circuits to perform the processing. A signal, by definition in electrical engineering, a signal is either a voltage or a current. A signal is a voltage or a current which varies with time. That is, a signal is either a time varying voltage or a time varying current, as simple as that. Which just any time varying voltage or current is not enough, which carries some information. That is called a signal. A signal is a voltage or a current which varies with time in such a manner as to convey an information. All right. For example, the current that you receive in a telephone receiver, it varies with time, and that is what is converted or transduced into sound, and that's how you hear the telephone conversation. So that is a signal. Or the ones and zeros, or the dashes and dots in a typical telegraph system, the Morse code, these are time varying voltages or currents which carry information, and therefore that is also a signal. Something interesting at the door? Okay, why don't you open? So a signal is a time varying voltage or current which carries some information. That second part is important. It has to carry an information. Any time varying voltage or current is not enough. Also, no voltage or current which does not vary with time can carry an information. A steady current or steady voltage, for example, doesn't carry any information. So that is not a signal. It is important to distinguish between signals and non-signals. All voltages and currents are not signals. Alright? In order to qualify as a signal, it must be time varying. First qualification. Second qualification, it must carry an information or a message. As I said, the current in a telephone receiver or the Morse code that is transmitted along telegraph lines, these are all signals. And the question of processing a signal arises when the signal that is available to you, is not the desired signal. You wish to convert it to some other form. For example, if you are given simply the current in the telephone receiver, but that is not your desired signal. You want to process the signal so that it produces a sound. In other words, you wish to transduce the electrical signal into a sound signal, and that is the form of, that is the desired signal. So this, the telephone receiver or the microphone, that acts as a signal processing element. The signal may be very weak, all right. For example, an old record, for example, which has gone very weak, and you wish to amplify this, all right. The amplification is a processing. Or you might have a slowly varying signal like this, and you wish to find out where it is varying at the most rapid rate. Then what do? You differentiate the signal, all right. So differentiation is processing. Or you might wish to have the integrated effect of a signal. In other words, you might want to integrate a signal. Then integration is also signal processing. So anything that you do to the signal, another example could be that a signal is mixed with noise, which is almost always the case. A signal is the desired information. It is always mixed with some undesired information or noise. If you wish to separate the signal from the noise, then you have to subject the signal to a signal processing circuit which gets rid of the noise and retains the signal only. So these are the various examples of signal processing. We shall come to signal processing circuits later, but let's study some of the some of the common signal waveforms. A signal waveform is said to be continuous or so-called DC. The ordinate here could be either a voltage or current, all right, because a signal is a voltage or current, time varying voltage or current. This could be V or I. We shall not write this again and again. Excuse me. And the independent variable is the time. So a signal which remains constant, a voltage or current which remains constant for all values of time, this is called a DC waveform, or also called a continuous waveform, continuous signal waveform. But as I said, a non-time varying voltage or current does not carry any information. So in that sense, this is not a signal. It is simply a waveform, a DC or continuous waveform. Consider now a battery, let's say a voltage V, in series with a switch and a resistance R, all right. And suppose the switch is put on at time t equal to 0. Then if you measure the voltage across this V of t, and you plot the voltage V of t versus t, this is t equal to 0, then for t less than 0 it is 0, and for t greater than 0 it is equal to capital V. Isn't that right? So t greater than 0 it is equal to capital V. In other words, the signal now, the voltage rises from 0 to a value capital V abruptly at t equal to 0. Such a waveform is called a step waveform. Step. It does look like a step in a staircase, all right. And as I said, it could be the voltage or the current. If you measure this current I, obviously the current I shall also be of the form of a step, all right. I would be equal to simply V by R, V divided by R. So the current as well as the voltage in this circuit shall be a step. If the amplitude or the height of the step is unity, if this is 1 volt or 1 ampere, then you call it a unit step, all right. A unit step therefore is a function which is 0 for t less than 0 and which rises to 1 at t equal to 0. And this function is given a special name of unit step function and is denoted by u of t. This symbol u is reserved for a unit step. and therefore the voltage in the previous case, in the previous circuit, which had a step of height capital V, if you have a voltage waveform of height capital V, voltage step, V of t versus t, then obviously V of t can be written as capital V times u of t. Alright, u of t is the unit step, and this symbol is more or less universal. We shall reserve the symbol small u for unit step. It could be a voltage, it could be a current, it could be a force, it could be an acceleration, it could be anything. But u simply stands for unity height. And when you write u of t, it means that the abrupt rise or the step occurs at t equal to 0. T equal to 0 minus it is 0, at t equal to 0 plus it is equal to unity. This is the symbol that is reserved for this. Now suppose we have a battery, consider another circuit, a battery in series with a switch and then an R, a resistance R. You measure the voltage Vt across the resistance R or the current that is flowing through R. They are simply related by Ohm's law. And what you do is you operate this circuit on and off. Let us say that it is on for 0 to, let's say, t1. Alright, that is, it is put on at t equal to 0. Then it is kept on up to time t1. Then it is put off, that is t1 to, let's say, t2. Then again maybe it is put on, let's say t2 to t2 plus t1, and off from t2 plus t1 to some value you calculate. Alright, suppose this goes on, that is, this switch is put on for a time t1, then put off for a certain period of time t2 minus t1, then again put on for t1, again put off for t2 minus t1, and so on. Suppose it goes on doing this. Then what would be the waveform? What would be the shape of the signal? If I plot V of t versus t, then we shall have for the on period the voltage shall be V. For the off period the voltage shall be 0. Again for the on period voltage is V. For the off period the voltage is 0, and so on. Such waveforms, they look like rectangles. They are called pulses. Pulses. So this is a pulse waveform. And you have seen how it can be generated. Pulse waveform. This is also a special kind of signal, which is, it is a signal because it is time varying. And if you call the on pulse, the on voltage is 1 and the off voltage is 0, then this forms the basic waveform of a digital computer. A digital computer, after all, works on the basis of just two levels of voltage or current. One level is called 1 and the other level is called 0. Ones and zeros. Alright. So a pulse is in the heart of operation of a digital computer. There are other kinds of waveforms which are also of interest. For example, you have a waveform. Once again, let's say this is a voltage waveform. You have a waveform which rises linearly up to a certain instant of time, and then it falls abruptly. Okay. Then again it rises linearly, falls abruptly, and so on. This waveform looks like the teeth of a saw, and therefore it is called a sawtooth waveform. Sawtooth waveform. It's just that similarity. There is no other interpretation associated with this. Now, a sawtooth waveform is extremely useful in a cathode ray oscilloscope, in CRO. The electron beam that you see on the face of a CRO. Have you seen a cathode ray oscilloscope?
Yes,
you have. The electron beam that you see, well, it starts from the left end. It starts from the left end, goes linearly across the screen, and then in almost 0 time it comes back. So it's coming back, you cannot see. Alright, then again it goes back like this, then again comes back like this. This is the waveform to which it is subjected. That is, the electron beam is subjected to a force which varies like this, and therefore it goes linearly up to a certain point, then comes back immediately, again goes, again comes back. The TV scanning is also done exactly by a similar waveform, a sawtooth waveform. The other kinds of waveforms which are useful in electrical engineering and electronics are the exponential, and the other one is sinusoidal. An exponential waveform simply varies exponentially with time. For example, you could have a v of t which is v e to the power at. Alright, it's an exponential, that is, it varies as a power of e. Well, if a is 0, then you see it is a DC or a continuous waveform. If a is greater than 0, then it is a growing waveform. If a is positive, then with time t, the amplitude or the value of the voltage continues to increase. Alright, if this is, let's say, t equal to 0, this is t, then when a is greater than 0, it is a waveform like this. At t equal to minus infinity, it goes to 0. As t goes, what is the value here? This is obviously capital V. Alright, when t equal to 0, it's capital V, and then it continues to rise. So this is called a building exponential, an exponential which builds or which grows. Building or growing exponential. Alright, that is a better term, I suppose. Growing exponential. On the other hand, if A is negative, then obviously the exponential will be a decaying exponential. If A is negative, then you see what happens is it decays like this. Again, let's say v of t equal to v2 e to the at, then this voltage, this level shall be equal to v2. Alright, this level is v2, and then as t increases, it decays. So this is called a decaying exponential. Well, these are not hypothetical quantities. A growing exponential and decaying exponential occur very frequently in circuits, in electronic circuits, and also in passive circuits. For example, let's consider a capacitor which is charged to a voltage, let's say V. Alright, a capacitor C which is charged to a voltage V, so the charge in the capacitor shall be equal to C times V. Let's have a switch here and a resistance here R. The switch is closed at t equal to 0. At t equal to 0 minus, the charge is Q. Let's call this Q0. Q0 is the charge on the capacitor at t equal to 0 minus. Alright. So, Q0. Alright. Let's use a different color. At t equal to 0 minus, the charge is Q0, and when the switch is put on, the charge on the capacitor now finds a path for flowing. Capital R, this resistance allows a path to flow. If the voltage is V, then obviously the current through the capacitor shall be V by R. And you know, when current flows through a resistor, heat is generated. So the resistor consumes energy, and therefore the charge in the capacitor decreases. So does its voltage, and this decrease, as you shall see later, is exponential. The decay is exponential. Alright? Or let's say we have a battery V, we have a switch, and then we have a resistance, and then we have the capacitor C. Suppose we measure the voltage across this V of t across the capacitor C. This is resistance R, and this switch is put on at t equal to 0. Alright. At t equal to 0 minus, that is when the switch is off, the capacitor voltage is 0. Capacitor has no charge in it, so the capacitor voltage is 0. So if I plot the capacitor voltage V of t equal to 0 minus, it is 0. Then at t equal to 0, the switch is on. The capacitor cannot change its energy instantaneously, and therefore t equal to 0 plus, the voltage across this will still be 0, and therefore a current V by R passes in this circuit and tends to charge the capacitor. As soon as it accumulates a little charge, a voltage appears across it. And as it continues to accumulate charge, the voltage across the capacitor rises, as you shall see, exponentially. And if sufficient time is allowed for the capacitor to charge, the capacitor will ultimately charge to a voltage equal to that of the battery V. That is, in the equilibrium condition, when the capacitor has been fully charged, the current in the circuit shall be equal to 0, or the capacitor voltage shall be rising to a value of capital V. Alright, so this is a case of a growing exponential, and this is a case, the previous one was the case of a decaying exponential. In exponentials, as I said, if I consider a decaying exponential, let's say Vt equal to V e to the minus at, let's make it specific where a is greater than 0. Alright. Suppose we wish to find out the value of time at which V of t, you see V of t diminishes with time. It starts at capital V and it diminishes with time. Suppose we want to find out the current at which the voltage reduces to V by E, that is the eth fraction of the original voltage. Then let's call this time as T1. So T1 would be given by V by E equal to capital V e to the power minus AT1, and therefore we shall have e to the minus 1 as equal to e to the minus AT1, right? V and V cancels, 1 by E is e to the minus 1, and therefore 1 should be equal to AT1, or T1 should be equal to 1 over A. Alright? This time T1 is given a special name. It is called the time constant of the exponential waveform, and is denoted usually by capital T, the time constant. And therefore, in terms of the time constant of the exponential waveform, we could rewrite our exponential waveform as V e to the power minus t by capital T, which makes it obvious that when small t is equal to capital T, then the value of the waveform shall be equal to V by E. Alright. It is a matter of simple calculation to show that a waveform, like an exponential waveform like this, e to the minus t by t, let's consider the normalized waveform. That is, the normalized with respect to the value at t equal to 0. Alright. In other words, Vt by V is the normalized, and it starts from 1, then it decays like this. Alright. It's very simple to show that if t is equal to 5 to capital T, then the value Vt by V decays from 1 to e to the power minus 5. That is 1 by e to the power 5, which is approximately equal to 0.0067, less than 0.7%. Alright, less than 0.7%, which is approximately, which is smaller than the accuracy of the ordinary instruments available in the laboratory. If this is a voltage, you cannot measure a voltage to an accuracy less than 0.7%, and therefore 0.0067 is, for all practical purposes, can be taken to be 0. And this is the reason why electrical engineers say that an exponential waveform has a lifetime of 5 times the time constant. Is the phrase understood? It's very loosely said, it's not exactly 0, but since the value is less than the accuracy of an instrument available in the laboratory, we say that for all practical purposes an exponentially decaying waveform has decayed to 0. It means it is dead after 5 times the time constant, and that's why we say the lifetime of an exponentially decaying waveform is approximately 5 times the time constant. Exponential waveforms are extremely interesting. Not only they are important, they are also very interesting, because as you know, d dt of an exponential waveform e to the at is also exponential. Isn't that right? Integral of e to the at dt is also exponential. It is e to the at divided by a. Alright? Indefinite integral. So this makes life very simple to work with exponential waveforms, as you shall see later. And to illustrate the importance of exponential waveforms, let us consider an example. I have a current generator which generates at 2 times e to the minus 250 t milliamperes. Okay, current generator which generates not a constant value, but it varies with time. Therefore, it's a current signal 2 e to the minus 250 t milliamperes. What is the time constant? 1 by 250. That is 0.004. Okay. And this is passed through a series combination of a resistance R, which is 3K, and an inductor L, which is 4 Henry. What you are required to find out is VR, that is the voltage drop across R, VL, voltage drop across L, and the total voltage V across the combination. Alright. As you can see, VR is simply IR. It's simply the current multiplied by R, and this is milliamperes, this is kilos. So it would be 6 times e to the minus 250 t unit volts. Do you understand why it is 6? 3K is 3000, and 2 milliampere is 2 times 10 to the minus 3, and therefore 3 times 2. Now VL similarly would be L, that is 4, di dt, that is times 2 times 10 to the minus 3 milliampere, mind you, we want to convert it into volt, times ddt of minus e to the minus 250 t, that will be minus 250 e to the power minus 250 t. Is that okay? Can you tell me how much is this? Minus 2 e to the power minus 250 t volts. Alright, so the polarity that is shown here is not the correct polarity. VL is negative, means that this end is positive and this end is negative. Alright, this is because the current is a decaying exponential, so d dt is negative, the slope is negative, and therefore V would be simply the sum of the two, and therefore this would be 4 times e to the minus 250 t volts. Is that okay? Similarly, we could have taken a capacitor and we could have found out the voltage across the capacitor by taking 1 by C and then integral of I dt. That would also have been an exponential. This is the beauty of an exponential waveform, that an exponential signal generates in linear circuits. If it is non-linear, then of course you have complications. But in a linear circuit, an exponential signal input produces exponential signals as output, because integral and differential of an exponential is again an exponential. Finally, we consider the most important waveform of all, that is the sinusoidal waveform. A sinusoidal waveform is very much a practical proposition, because if you take a coil and rotate it in a constant magnetic field, then you know that a voltage and EMF is generated in the coil which is sinusoidal. So electricity generation at generating stations, the generated waveform is sinusoidal, and a sinusoidal waveform in general. Can you give me another example of sinusoidal quantity in any other field? It doesn't matter whether it's electrical or non-electrical.
So simple harmonic motion.
Simple harmonic motion. Who executes a simple harmonic motion?
Pendulum.
A pendulum. A damped pendulum or an undamped pendulum? Undamped, obviously. A damped pendulum, all that you have to do is to add an exponential term. A damped pendulum will execute oscillations of this form, sine omega t plus theta. The exponential term, if it is included, then this takes care of the decay in amplitude. That is, the pendulum gradually executes smaller and smaller arcs. All right. Therefore, a pure sinusoid, to bring variety into experience, let's say we now consider a current I of t, will be of the form capital I, sometimes we call it Im, sine of, let's say, omega t plus alpha, let's say. It could be sine or it could be cosine, all right? Or it could be, let's say, v of t is equal to some Vm cosine of, let's say, omega t plus alpha. Sine or cosine, it doesn't matter. Both are sinusoidal. There is a favoritism in favor of sine. We don't say cosinusoidal because it uses more letters. CO is to be added. That's all, economy. So we say sinusoidal. Both are sinusoidal. Now, the various parameters of a sinusoidal waveform are, firstly, this quantity, which is called the peak value. Obviously, this is the maximum of the right hand side, because sine can either be, the maximum value is 1, and therefore Im is the maximum value. So Im is called the maximum value or peak value, PEAK, or simply called amplitude. Amplitude. These are the three names by which it can be called. Omega is called the frequency in radians per second. In radians per second. You know, a particle executing simple harmonic motion can be described by another particle revolving around a circle. So the number of complete circles it executes in 1 second is the frequency in radians. Okay, omega is the frequency in radians per second, t is the time in second, and alpha is called the phase, or sometimes, well, the actual nomenclature should be initial phase. That is when t equal to 0, mark these words carefully. When t equal to 0, the angle is simply alpha. That's why alpha is called the initial phase, or sometimes loosely simply the phase. Actually, phase stands for whatever the argument of sine is. That is, the total quantity omega t plus alpha is the phase at time t. Alpha is the initial phase, but loosely it is often called the phase. The sketch of a sinusoidal waveform, let's say Vm cosine of omega t plus alpha, is very familiar. It is something like this, where this amplitude is Vm and this is minus Vm. The maximum in the positive direction is plus Vm, the maximum in the negative direction is also the same, it is minus Vm, and this value would be Vm cosine alpha. This is t equal to 0. What is the value of time corresponding to this? Obviously, okay, if this is omega t, then this would be minus alpha. Agree? What is the difference between this time and this time in terms of omega t? What is the difference of omega t between this point and this point? Pi by 2. Alright. So, what is this value then? Pardon me? Minus alpha plus pi by 2. Wonderful. And what is the difference between these 2 points? That is the point at which 2 pi. Omega t equal to 2 pi. So, if I denote the corresponding time by capital T, then omega capital T is equal to 2 pi. And what is capital T? The time period. And what is the relation between time period and frequency? Inverse. And therefore, if we say that this sinusoid has a frequency of f in cycles per second, capital T is the time for one cycle, so the number of cycles per second is 1 by t. So if we say f is the frequency 1 by t, then the unit of f is cycles per second or hertz. Alright, and so omega is 2 pi by capital T, because omega capital T is 2 pi, and therefore this is equal to 2 pi f. Omega is in radians per second and f is in hertz, after the name of Hendrik Hertz. To illustrate this sinusoidal will be your bread and butter in this course on Introduction to Electronic Circuits. It will also be extremely useful in the course 120, which is electromechanical energy conversion, in which you will see that all generators generate sinusoidal waveforms. All right. Then what you do with it is somebody else's business, but originally you always generate a sinusoidal waveform. Let's take an example, a non-trivial example. I warn you. The example is on sinusoidal waveform. Express the following sinusoidal signal as a function of time. The description of a sinusoidal signal is given. You have to express it as an equation or as an expression, and the information that is given is the frequency is 100 hertz. Okay. Amplitude is, let's say it's a current. Amplitude is 10 milliampere, and this is I of t, and it passes through, these are the information that is supplied, passes through zero value with positive slope, at t equal to 1 millisecond. This is the information that is supplied about the waveform. You have to write an analytical expression for this. What are the things given? The frequency is given, the amplitude is given, and about phase, obviously what remains is the phase, isn't it? About phase or the initial phase alpha, the information that is given is that it passes through 0, the value of the waveform passes through 0 with positive slope at t equal to 1 millisecond. Alright. So I can write my I of t as 10 times 10 to the minus 3, always normalized, always in terms of SI, 10 milliampere. Then would you use a sine or a cosine? We have not been asked, we have not been told, so we can use anything we like. Let's say we use a cosine. Cosine of omega t, omega is now 2 pi times 100, which is 200 pi t. All that remains to be found out is alpha. Alright? And it has been told to us that the value is 0, the value is 0, IT is 0 at t equal to 1 millisecond with positive slope. Now the importance of positive slope and negative slope, you can see that a cosine waveform is like this. Here at this point it is positive slope. It passes to 0 with positive slope. At this point it passes to 0 with negative slope. So it is this point that is given. Alright. Now what is the condition for positive slope? Let's take a cosine of omega t plus alpha. d dt of cosine omega t plus alpha is minus omega sine of omega t plus alpha. So if the slope is to be positive, it's not a trivial question, you follow this carefully. If the slope is to be, if ddt is to be positive, then obviously sine must be negative, because there is a negative sign here. When is sine negative? When omega t plus alpha itself is negative, and therefore the condition that IT equal to 0 at t equal to 1 millisecond with positive slope implies that this quantity should be equal to minus, this quantity should be negative, minus pi by 2. That is correct, which will now give away alpha. That is, our condition will be 200 pi 1 millisecond, so 10 to the minus 3 plus alpha should be equal to minus pi by 2. Is that clear? How we found this information out? We argued that the argument omega t plus alpha must be negative, and since cosine is 0, the value must be minus pi by 2. And therefore alpha is equal to, this is minus 0.5 pi, and this is 0.2 pi, so minus 0.7 pi. Is that okay? And therefore my final answer is 10 to the minus 2, 10 into 10 to the minus 3, cosine of 200 pi t minus 0.7 pi, so many amperes. Alright, this is the final answer. Be careful about handling sinusoidal quantities. They, depending on the slope and other information, it's very easy to make a mistake. Now sinusoidal waveforms are a special kind of waveforms which go by the general name of periodic waveforms. Periodic. Periodic waveform. A function f of t, we will not use f of t because small f we have used for frequency. A function x of t is said to be periodic, if x of t is equal to x of t plus nt, where capital T is a constant and n is an integer, positive or negative including 0. X of t is said to be periodic. The qualitative meaning is that x of t values repeat after every regular interval, and this interval of repetition is said to be the time period. So capital T here is the time period, and n is an integer. N is an integer. Obviously n could also be 0. X of t is obviously identically equal to x of t, and n could be any other integer, positive or negative. For example, a cosine omega t plus alpha is periodic because it is equal to a cosine omega t plus capital T plus alpha, where capital T is equal to 2 pi divided by omega. It is therefore a periodic waveform. Now a periodic waveform, because it repeats after regular intervals, how do you measure a periodic waveform? How do you devise a meter to measure a periodic waveform? There are various kinds of measurements. For example, you wish to see the periodic waveform, then you have to display it on a cathode ray oscilloscope. That displays the total waveform, that is a cosine omega t plus alpha. Alright. Now, if you want a parameter for the periodic waveform, there are various parameters possible. For example, one could think of the average value. Now, the average value is always spoken of with regard to one period. Alright, average value is over one period. What is the average value of a sinusoidal waveform then?
Half of the
Average value of a sinusoidal waveform? 0. If you take a sine omega t, for example, the average value equal positive, equal negative, and the average value is 0. However, if I take, let's say, a triangular waveform like this, a symmetrical triangular waveform like this, let's say this is 0, t, and let's say I of t. Alright, what is the average value? Suppose this is Im, yeah? Im by 2. This is the time period, and therefore the average value is Im by 2, half of the peak value. In general, the average value of a periodic waveform, let's say I average, is equal to integral, you integrate over one period 0 to t, I t dt, and divide by capital T. This is the average value definition. Now, does it matter whether the lower limit is 0 or some other value? Can we have t1? Yes, then the upper limit should be t1 plus t. You can start anywhere, but you have to end after an interval of capital T. So this average value is independent of small t1. Alright. Now, since in a sinusoidal waveform the average value is 0 counted over one period, in a sinusoidal waveform the average value is usually calculated over half a period. So for a sinusoidal waveform, I average is calculated over half a waveform. That is, you take half of the waveform, the positive cycle, find out the area, and then divide by t by 2, and you can easily show that this is given by twice Im divided by pi. You can easily show. You take sine omega t, for example, integrate from 0 to t by 2, then divide by 2, which is equal to 0.637 Im. You must remember the definition of the average value for a sinusoidal waveform. If you take over one period, it's identically equal to 0, so you always speak of half a period. Next time would be Monday again, isn't it? This Friday is a holiday. Oh, I see a smile on the face. So Monday we shall talk of other kinds of parameters for periodic waveforms. That's all.